Okay, so we can start. The title of today's talk that we will be presenting is improved lateral and depth positioning using depth imaging technology. Today we're going to actually have a two parts talk about this subject, and the first part will be actually in the depth itself in general, and then the later one the talk that will follow will be about diffraction imaging. So stick to this channel and GOL. Okay, so let's start with this improved lateral, the first part, improved lateral and depth positioning using depth imaging technology. So first question, what we need to answer, why we are imaging in depth domain. Typically, not typically, but all geological engineering reservoir modeling studies, they have all developing their models in depth. The only guys that are on the G&G team that are actually kind of related to time is the seismic data and the seismic interpreters. So by translating the seismic interpretation and all the models that are developed from time to depth, will actually enable the integration between the seismic and assets and the geological and petrophysical and production data all together. So it will enable that we can actually really communicate better, and then as a result of that, we can actually reduce our drilling risk in the subsurface. Okay, especially when you are dealing with the harder and then the more complex structures. So normally when we are recording in time, seismic, and acquiring the data, the vertical scale that we have, it's time. And then we do have some challenge there, right? So normally the Earth is in depth, right, as a vertical scale. And then if you have a true structure that has some, maybe let's say, thickening of the fast material, so when we record everything in time, we are starting to get the apparent structure. So that is not correct in time domain. So then we need actually to reveal to go from time domain into depth domain and then reveal the true structure from apparent. So as a consequence of that, when you're doing so, then if you have a good conversion from time to depth, then you can actually reveal the true structures, and then you can reveal eventually that potentially bypass the reserves that you have, right? So as on the image side, so in the time domain, you might actually see sags and the pull-ups. And then when you are having the correct velocity, that it's actually the good conversion, that it's key to the good conversion. So then you can actually reveal the true distance. So when we are talking about velocities, there are many choices that you and then depends on the lateral model that you have, or lateral vertical model. Is it 1D, is it 2D, 3D models, right? So there are different approaches we can take, and then some of them, they have a pros. Every actually has a pros and cons, right? So, for instance, if we can talk about data types, we have a check shots, logs, VSP. Typically, these are 1D data, right? You can divide them as a model types, volume based, horizon based, or even you can use a hybrid combination of those two, right? Then the velocity type, when we are talking, we have a different type of the velocities. It can be average, interval, RMS, stacking velocities. So on the model strategy, how you implement the conversion from time to depth. So you can actually talk about, is it just you can put one function to apply across the, or you can have a kind of a gridding in a 3D sense. You can actually guide this 3D gridding with the geostatistical gridding as well, so we can actually introduce some other data that can actually drive the gridding. You can use tomographic updates from the instead of let's say single function. Then you can talk about model. Is it isotropic, anisotropic, and then is it coherence inversion? So there are different strategies you can apply. And then you can actually use, okay, so you can discuss, are we doing this with just a pure vertical stretch that you can actually just deal one beam at a time, or you can actually just do the whole map, which will be like a 2D migration, or you can actually go in a full PSDM migration that you develop the model and then you do the volume migration conversion from time to depth. So some are faster, obviously the going with a PSDM approach. So you should be actually being the most accurate one, because that's all measured in a pre-stack domain, and then using all the gathers, and then obviously it takes more time to do this, right? That effort. Okay, the main objective for the depth imaging then, that shouldn't be just a seismic image to be a good imaging, right? But it has to be the correct image too as well. Then you have to have developed the correct that will actually reveal the correct dip, not the one that you have apparent dip that you are actually having in the time domain. Then it should be the correct depthing. So the depth of the horizon should be correct. And then obviously, if this is all good, so you should be actually having the good well ties as well. So whatever you are drilling, so and then all your tops from the wells should be actually meeting the ties and then the tops of the wells. Right? So typically, it is done in 3 phases. The first phase should be data loading and then QCing everything, just learning about the data and then all the challenges that the time processing went through. So the next phase should be velocity estimation and modeling. So creating through the multiple passes, you are actually creating a velocity model. And then once you have the velocity model that we are happy with, then we can actually choose the proper or what migration we will proceed with the migration, the final migration, and then there are multiple options depending on what geological setup we are in and what the challenges we have. Okay, so let's start with the data loading. First of all, what we do, we actually get through the data, so making sure that we understand everything what's going on in the data. So including fold maps, elevation, inline, crossline offsets. We write some rows diagram just to see what the average patch was actually applied, and then what offsets to be used. So then we can, if you're dealing with OVT, so we can create all these maps that are actually making sure that we are actually parameterizing correctly, where you have the maximum fold and then all coverage within the data set. So these are all that when we are scanning, we are actually learning about the data that what happened in the time processing. Okay, so that will help us to put the correct parameters in our model building and then migration after, right? So also we can actually define we are making sure that we are choosing correctly the offset groups that we're dealing with. We can create the maps and we can look at the lateral distribution of each group. So if you see the holes, obviously we would like to have as least the small number of holes to cover everything, so all bins across the survey. So once we learn everything about that, so then we can actually continue with our model building workflow. So in a brief, so what we are supplying, we can actually supply some kind of input data that we need actually to develop some initial velocity model, right? That's the first step, right? To build it, and then you can actually start from RMS and then sonic logs, 1D or 2D data or volume. So this is the one. So we build an initial velocity model. So once we have that, so we supply our time gathers, and then with that model, so we can actually run initial pre-stack time migration. And then we come up with the gathers, and that's initial PSDM gathers and PSDM stuff. Since that we are not, this is just initial model, so we expect this gather not to be flat, and then PSDM stack not to be the most optimal. Okay, so we're gonna talk about this first part, right? So I'll come back to this other parts. So we'll go through the workflow. So in the process of building the initial velocity model, so first of all, we have to build a strategy. How are we gonna access this? So we gotta actually look at what kind of data we have. We have to analyze just the data, so which is good, which is what we are confident in data. So from the whole database, how well they are distributed around the server laterally, so we would like to see what information it's available beside the seismic itself, right? We can cross-plot them, and then we can do the analysis, edit, or whatever. So then later on, we have to choose, depending on the geological setup, what we have. Are we going to apply the strategies of the horizon-based, volume-based, or maybe you can do the hybrid, as we said in the previous, so we can actually combine it. So, and then at the end, so we would like to make sure that we can actually just, as we are getting closer, so how to do correct the computation, right? So are we just applying the single scalar, or we would like to do this well-type tomography, right? So depending at that time when we get it. So this is more like a strategizing before it comes. So to start with the initial velocity, so there are a few methods we can apply to it. And then if you have, let's say, we don't have any other information, let's say, so we can actually rely on the velocities that were actually developed in the time domain. That's RMS velocities in time. And then in that case, we know that Dix transformer will actually convert this straight from internal velocities in time into internal velocities in depth. But obviously, if you just apply the pure math on that, so you will see that will be like a more jittery reaction to that, right? So the solution, right? So instead of that, we would like to have, we are applying the CVI, what we call it, it's a constrained velocity inversion we are using. And then we are able actually to create a smooth and geological credible velocity volume. So that will make sure that we can actually have all locations and everything, it will be transformed into the regular fine and geologically constrained internal velocities. So you can see they can start to reveal some geology as well, some layering. And then that's how we actually create the internal velocity model. Okay. So the other question comes as well, since that in the time domain we developed refraction statics, so there is option as well. So we can apply that. So we can actually incorporate the refraction statics that were developed through the time processing, or not. So depending how severe the near surface is, or elevation changes, or so if you're so we can actually make a decision on that. Then if you have a logs and a good distribution across the surface, so we can actually start with the building the velocity model, even without using the RMS velocities for time, we can actually just go straight from the logs that we have. So it's for that purpose. So in order to do this correctly, so probably we actually will need a good distribution, lateral distribution. And then we have, that doesn't matter how many well locations you have, the more you have, of course, it's good, but the key point is to be nicely distributed across the survey. And then we can use this with the geostatistical grading. We can use this techniques to develop something that it's a direct measurement on each of these locations, right? So we can develop the volume using those information. Okay, so this is the few methods that how to actually get to this internal velocity model, right? So Okay, the second block. So once we have this PSDM stack, so what we can use, we can actually extract the structure attributes out of that. So that will actually help us later on in the tomography, that we can actually constrain our solution. So extracting attributes are deep, azimuth, and continuity, what we call it DAC. And then this can be actually used in a tomography as a source location for shooting the rays. And then this tomograph that will enable that our tomographic solution will comply with the geological structure underneath. So because we're going to be shooting more realistic ways, not just a pure mathematics approach, right? So basically, what we have in a deep structure, so you can see that on this image. So let me see if I have. So you can actually see that you can actually those attributes that do follow the structure, and that's actually are making sure that the solution that we are providing, it's actually constrained with the structure that we have under. So by doing that, so then these are the points that were developed out of this, and then these are in black here. You can actually see that that's a location where we are actually shooting the rays. Obviously, we would like to shoot wherever we have a good continuity, and that means that we have a reliable data. And then on this side, so you can actually see this is continuity in this data set. This is a continuity data set, and on the other side, it's a dip. So you can shoot in a particular dips your rays. It will follow that. And of course, you can look at correlation in the gathers as well. Okay. So these are the attributes that we would like to develop, and then using them as the side input to tomography. Okay, so these are about these structure attributes that we will be putting in the tomography. On this block here, after the PSDN gather for after the initial model, so we are actually going to, after the first initial, we don't expect them to be flat, but be somewhere closer to flat, let's say. And so we need actually to pick some residual velocity analysis, travel time errors to find, and then we supply those into the tomography along with the structure attributes. We create a new velocity update, and then we run migration, and then we create a new PSDM gathers and stack, and we'll look at the gathers, and then we can actually judge if they're flat or not. If they're not, then we can reloop the process a couple of times until we have a flat gathers. Okay. So to do this, so we can actually, as we said, we can discuss about in a strategy if you're using the grid or base model tomography update. So what approach we're going to take? There's pros and cons as well for those. So these grid bays are actually more suitable for the less complex structure when we are not confident with our structure model, because that's kind of a driven, right? If you're imposing the model, so that means you have some prior knowledge and that you understand what's going on there. You don't want to put the model if you're not confident. And all the updated cells will be equally, in the lateral sense, will be regular updates with the same size, and then you can vary the size in the depth domain, but it's completely irrelevant of the structure itself, right? So on the model side, so you can do exactly the same, except that the solution will fully comply with the geological structure, because this will be now in this case in the model base, the updated cells will actually stretch from horizon to horizon, and that will be the full update grid. So it will be a variable, vertically variable updated grid, but that will be actually complying with the geological structure. So this is two options we can choose in the strategy. So obviously there will be so if you're just this is how the structure the output solution will look like. Initial will be more smoother, right? If you have that's just a smooth just from the first conversion. Then when you have a first update, let's say on the grid base, it's going to look a little bit more start to reveal, but the geological layering, but not as much as when you are using the formation attributes, that's DACA. So now when you're doing just a modular based, so then it's really impacting that you're actually imposing your model into this. So this is the kind of a solution what you should be expecting, and obviously in our processing workflow we combine all of those. Okay, so we can actually, when we are doing the estimation on the travel time errors, we can actually be in the horizontal or vertical mode. Then when we are picking in a vertical mode, we can actually pick the residual velocity. So and then that's a normal, like a standard approach. But what we can do, we can actually making sure that we can pick along the horizons, right? So we can actually develop the semblances, and then we can actually pick just along the horizon. So making sure that we are consistent in the velocity and don't have ups and downs, jitter on the velocity, so then it doesn't actually create that your horizon goes ups and down. So we can actually use this along the horizon, so we can actually create peaks that are really consistent with the horizon. So when we're doing the residual. Okay. So we can actually use as well automatic residual velocity that will be as well ABO compliant. So you can we can develop for a velocity that residual velocity field that it's actually picked every sample in the lateral and the vertical domain, and then you can actually use that. For that, obviously, you need a little more better signal to noise ratio. But yeah, we can develop that. So it's a high density and high resolution velocity analysis we do. You can actually use as well the other is a non-parametric approach. That the non-parametric approach is the approach where you actually will pick your horizons, your events. You will be picking based on your DAC attributes. So wherever you have a good signal to noise ratio, wherever you will be shooting the rays, so that's where you would like to pick it, and then as opposed to the parametric, you don't fit parabola into it. We just pick the individual traces, and then by doing this, so you will be able actually to develop. This is automatic picking as well, and you will be actually developing a few parameters, attributes that will be actually describing the quality of your picks, and based on those, you can actually eliminate some outliers and then bad picks. What the idea about that is to put into the tomography only the most reliable, and then the picks we trust, right? So the workflow for that part is, so we put those outside pick attributes, we run the auto picker, non-parametric auto picker, we QC them and edit, we create the pencils, update the pencils, that's a database that where these picks are stored. We run tomography update, pre-stack depth migration, and then we look at the gathers. That's the same thing as others approaches. Okay, so typically when we are doing this, so then let's see this by. Yeah, so we are actually looking everything in a 3D sense, so we can actually look at all the attributes that we have, and then velocities that were developed. We can actually as well look at in the other directions as well, inline cross-line direction. We can slice it. We can look at the 2D like a pre-stack and the post-stack data set at the same place, and you can look, for instance, every offset plane on the gathers, and then you can see the gathers across the survey as well. You can pick the mute, on the gathers, just to make sure that we are looking at the right things. So you can volumetrically display your residual peaks, right? This is the process of eliminating, and then you can correlate at the same time. You can say your animals, like residual velocities, and with those attributes, and based on those attributes, you can visually cross-correlate those information, so you can actually have a good QC and good look at the velocity analysis. And then at the end, so you can actually eliminate those, as I said, outlier information, outlying information that we are not confident with, and then we supply into the tomography. We supply the only reliable information. And then obviously when you pick, so you can display in the most standard way, so in a 2D sense. So you see that before was the curved velocity, there is some residual move out, and then after that it's much, this is after the first pass, so how much it corrected. So you can look at the few ways of that, so you can make sure that that everything is nice and then very well visually set, so we can actually make good decisions. Okay, so also just a note on the 2D data versus 3D data. So we are actually, if you're dealing with the 2D data, we are actually able to develop a pseudo 3D model, so they're making sure that all intersection, everything, so we can develop one velocity model out of all those 2D lines, making sure that there is no discrepancy in the velocities, in the intersections, and everything is nicely done. So when we are talking about well-timed tomography, and then we have two options within a tomography itself. We have a joint reflection and then refraction and reflection, so we can combine those simultaneously update, and then well-timed tomography as well. So for the well-timed tomography, so typically you get, I mean, after the processing, you get your flat gathers, right? Everything is flat. But when you actually put this developed model, right? So that and then migrated stack, so you might actually see that there are some discrepancy. And typically that should be because of you have some anisotropy. So your horizon might actually appear lower than your tops. And then since that your gathers are flat, and it says, okay, so how I'm gonna do this? So typically interpreters will be actually shifting this by scaling and then making sure that horizons will meet the tops. But we can actually do if you do this, so then your gathers are going to be not correct anymore. And then if you remigrate, maybe not, that's not going to create you the good response on the stack. So how to meet those things? So making sure that your gathers are flat, and then it's still maintaining the good ties. So this can be done by introducing the mistime maps, and then by introducing, we can constrain the tomography solution using this with maintaining the flatness of the gather as well. So if you remigrate with the new updated field using these maps, so then you will still have the flat gathers. So okay, so this is the short workout that we are actually converting the PSTM velocities into depth using this ISO velocities, the final ISO velocities, and then we do the tomography update, and then using these mistime maps, we review the ties, and then if there, so you can relook this a few times if you need it, and then we have that's updated field from the well-timed tomography, and then we can continue with the final reselect migration. So just the key points, so starting with the assumption that should generally be negative. That means that reflectors appear deeper than their true location. And this is because if the model is really anisotropic, so then that's what happens. And then if you have obviously some prior knowledge that you can actually develop from the wells, so we can actually use this as a initial input model velocity, right? Okay, so also we can actually have a joint reflection and refraction 3D tomography, so that we can actually use the shallow and deep velocities that can simultaneously update it. So it will differently treat this information from the refraction model can be updated using the first breaks. And then the deep will be using those attributes that has been developed standard way for us. And then now, once you have this whole model done, so we can actually start choosing the proper migration algorithms. And then typically is the fastest, and that's what we are using during the development of the field. So it's a Kirchhoff migration, but on our disposal as well as our CRAM. This is like B migration part. We can use Y migration, right? So one wave equation migration, RTM, or diffraction imaging that we're going to discuss in the next talk. And then I'm going to show you just a few examples. This is the legacy model that was there. So, and then that's a PSTM. We have the key was here, how to image those steep dips. And then as you see in the time domain, there is a problem how to develop those. But we were actually able in the depth to really to nicely image this. And that's, the client was happy with this. And then this is another example. And that's an image that was got from the PSTM. And then this is what we were able actually to develop all these steep dips using this. So that's the key sometimes for the structured data to go with the depth imaging, because now velocity models are all driven by the structure, and then all these again are using those structure attributes as well, constraint. Okay, thank you very much for the. So I'm now opening the floor for the questions.